Okay, so today we're cracking open the periodic table to look at one of chemistry's biggest rivalries. I want you to imagine two giant families with completely opposite personalities. You've got the metals on one side and the nonmetals on the other. So let's dive in and see what makes them so fundamentally different.
Just take a look around you right now. The very device you're watching this on, a spoon in your kitchen, even the air you're breathing. Every single thing is made of elements that fall into one of these two camps. So is that copper wire a metal or a nonmetal? What about a piece of charcoal? You know, understanding this basic divide is the key to, well, pretty much everything.
First up, let's talk physical properties. This is all about how they look, how they feel, and how they behave out in the real world. It's kind of like their first impression, before we get into any of the complicated chemistry.
So the most obvious difference right off the bat is their shine, or what chemists like to call luster. Metals, like the gold and silver you see here, are famous for being shiny and reflective. Nonmetals, they're usually pretty dull. But chemistry just loves to throw us a curveball. Take iodine. It's a nonmetal, but it's got that classic metallic shine. Pretty cool, huh?
All right, next up, what happens when you hit them? Most metals are both malleable and ductile. That's just a fancy way of saying you can hammer them into super thin sheets or stretch them out into long wires, just like the copper in our power lines. But if you try that with a nonmetal like a chunk of sulfur, it'll just shatter into a million pieces. They're brittle.
Now for a huge one, how they handle energy. Metals are fantastic conductors of both heat and electricity. It's the whole reason your cooking pots are made of metal and your electrical cords have copper inside. Nonmetals are the exact opposite. They're insulators. But once again, chemistry gives us this total game changer. Graphite. It's just carbon, a nonmetal, but it conducts electricity like a champ.
And get this, even within the metal family, you find some really weird characters. We think of metals as having crazy high melting points, right? Well, then there's gallium. It's a solid metal, looks kind of like aluminum, but its melting point is so incredibly low that your own body heat will turn it into a liquid silvery puddle right in the palm of your hand.
Okay, so we've seen how they look and act, but now let's see what happens when things get reactive. This is all about their chemical personalities, how they interact with other elements. And believe me, this is where the real drama begins.
So when metals hang out with oxygen, they form something called basic oxides. Like if you burn magnesium, you get magnesium oxide. Dissolve that in water and you've got a base. Nonmetals, though, they react with oxygen to make acidic oxides. You burn carbon, you get carbon dioxide, which dissolves in water to make carbonic acid. See the pattern? One makes bases, the other makes acids. Total opposites.
We've seen them react with their environment, but what happens if we put these two rivals in the same room together? You might expect an epic battle, but what actually happens is way more interesting.
Yeah. Instead of clashing, they form one of the strongest and most stable partnerships in all of chemistry, the ionic bond. This isn't a fight. It's a transaction, a perfect deal where both sides get exactly what they want.
So here's the core idea. It all boils down to this. A metal has an electron it's dying to get rid of, and a nonmetal desperately wants to grab one. It's a match made in heaven. The metal donates, the nonmetal accepts, and in the process they become oppositely charged ions that are powerfully attracted to each other.
Let's walk through this with the most famous example of all, good old table salt. So in step 1, you've got sodium, a metal. With one electron, it's just eager to offload. Then in step 2, chlorine, a nonmetal, is ready and waiting to accept one. Step 3, the electron makes the jump. Now, in step 4, sodium is positive, chlorine is negative. And the result? Step 5, opposites attract, and bam, they stick together like magnets, forming sodium chloride.
Okay, so we know what metals are, we know how they behave, but where do we actually get them? I mean, they don't just pop out of the ground as shiny gold bars. We have to work for it. We have to extract them from rocks in a process called metallurgy.
Put simply, metallurgy is the art and science of pulling pure, useful metal out of the earthy, rocky compounds they're normally found in. We call those rocks ores. So really, it's like a massive, industrial-scale treasure hunt.
Now, key thing here is that not all metals are equally hard to get. It all depends on how reactive they are, which we can organize into this kind of power ladder. The metals at the very top, like potassium, are super reactive and cling on for dear life to other elements. The ones at the bottom, like gold, are much more chill and less reactive.
And that power ladder we just talked about, it directly tells us the best way to extract them.
For the super reactive metals at the top, you need brute force, a method called electrolysis, which is basically zapping them with a ton of electricity to break their bonds. For the mid-tier metals, like iron, we can use a clever chemical trick involving carbon. And for those lazy ones at the bottom, well, gold is so unreactive, you can sometimes find it just lying around as pure nuggets. No K.
Now for those middle-of-the-road metals, there's often a little prep work to do before we bring in the carbon. The main goal is to turn their ores into a simpler form, a metal oxide. And there are two main ways to do this. For sulfide ores, we use roasting, which is heating with lots of air. For carbonate ores, we use calcination, heating with little to no air. So two different paths, but the end goal is exactly the same. Get a metal oxide that's ready for the next step.
So we've figured out how to get pure metals, but what if I told you that sometimes pure isn't actually what you want? This is where we get to play alchemist, mixing metals together to create something even better.
And that's exactly what an alloy is. It's a deliberate mixture, a carefully crafted recipe, designed to give us a new material with superior properties. We're talking about making things stronger, or lighter, or rust-proof, or even just making them melt at a lower temperature.
You use alloys every single day, probably without even thinking about it. Brass and bronze are classics. Pure gold is actually way too soft for jewelry. It would bend out of shape, so we mix it with copper or silver to make it more durable. And of course, stainless steel, which is just iron mixed with carbon and other metals to stop it from rusting. A perfect example of a metal and a non-metal teaming up to make something awesome.
And this is not some new idea. I mean, just look at the Iron Pillar of Delhi. This thing is over 1,600 years old. It's been standing outside in the elements all that time, and it is barely rusted. It's an absolutely amazing testament to the skill of ancient metallurgists who created an advanced iron alloy long before modern chemistry even existed. It really shows you the timeless power of this science.
So, from ancient bronze swords to the modern superalloys in our jet engines, our ability to understand and manipulate metals and nonmetals has literally defined human history. It really makes you wonder, as we continue to mix and manipulate and master all these elements, what incredible new materials are going to shape the next chapter of our story.